In a programming language, when you're working with a variable, that variable at runtime becomes associated with some area of memory. And the lifetime of that area of memory depends on what kind of memory you're working with. Is it a stack variable? Is it a static or a global variable? Or maybe it's a dynamic heap allocated variable. Each of these areas of memory has their own distinct lifetime. And the lifetime of an area of memory isn't something you may have needed to consider before if you've been working in a memory-safe language such as Java or JavaScript or Python. But when you're working in a systems language like C, C++, or Rust, you need to be more intentional and think about this concept of lifetimes a little bit more carefully in order to understand the implications of what it is that you're trying to do and to avoid some unsafe possibilities. So let's talk about lifetimes and what we mean by this word because it's such a novel concept if you're new to systems programming languages. So what is the lifetime of a memory address? There are two key questions that will help you evaluate this. First, when is it safe to access some memory that's been allocated for some variable or that's been allocated? And second, when is it unsafe? When does it expire? When is it no longer going to be a valid area in memory based on its initial usage? So these are two questions that you can ask to give you a sense of what is the lifetime of some area of memory or some allocated space that's been assigned to a variable. Both of these answers are going to depend entirely on how the memory space is allocated and how it's deallocated. And the best way to think about these two concepts is to focus on how they work on a given space in memory or a given segment of memory. So we're going to start in this video by looking at hopefully the most comfortable and familiar segment of memory, which is the stack. And we know that in the stack, with our automatic variables that are local variables within a function call, their memory space or their addresses are going to be allocated and deallocated for us automatically, hence the name an automatic variable in C, when we call functions and when we return from functions. So these local variables, the reason why they're called automatic is because of this exactly. Memory is automatically allocated upon a function call and entry into that function evaluation. And then when it returns, this memory is deallocated and it's freed up for other function calls to make use of in subsequent lines of code. So the lifetime of an automatic variable in C is going to be once that variable has been initialized. And so this is slightly more nuanced than just allocated, and I'll come back to that in just a moment. And it will be expired once that variable is now out of scope, which if you declared a local variable or a parameter in a function call, that would be when the function returns. If you declared a variable in a nested scope, it would be when that scope completes. So let's talk about this safe after initialization. When you're writing a function in C and that function call gets evaluated, before jumping into the function, there is some memory that's allocated for a particular variable. But it's not, if you're just declaring a local variable, it's not initialized automatically for you. If it were a parameter, it would be initialized to whatever argument you gave to that parameter. But for a local variable declared inside of a function body, you need to explicitly initialize it yourself. So technically, we would think that the lifetime of a local variable of a stack frame is after initialization and up till its scope expiring. Right? So why haven't you needed to worry about this before? Well, in C, you can read memory addresses before they're safe to read, right? And we've seen this a few times. We'll see it some more examples of it in this talk. And because of this, you can read a variable before its lifetime has officially begun. You can read a memory address before it's safe to. And you can also read a memory address after that memory has expired, because in C, if you have a handle on a memory address, which we can get using the address of operator and computing memory addresses from pointers, we can have handles to memory addresses that their lifetime may have expired. It may not have never even started. And so if you try and do this and you get very lucky, you'll get a compiler warning or a compiler error. If you're somewhat lucky, the program will crash very quickly and predictably. If you're unlucky, the program may not crash for days, months, or potentially even ever. It may just you may just have some surprising results in various run scenarios. And this is why you have to be very careful with thinking through a memory address's lifetime before you access it. C is not a memory safe language as opposed to other languages that you have used, such as Java, TypeScript or JavaScript, and Python. These are memory safe languages that don't allow you to access uninitialized variables, that don't allow you to access something that's been deallocated and has fallen out of scope, right? With a memory safe language, you have some guarantees. If you're able to read it and it's valid, you're going to get back a valid value. It may be 0. You may not have initialized some variable, but you'll get back 0, and that's okay. You're not seeing some junk value. It's predictable and it's safe to access that. If it's an invalid access, such as maybe in Java, you're trying to access an address off the end of an array, you will get an exception, and you'll have an error that's raised in your program. You won't just magically sometimes be able to read the contents that are off the end of some array, but you can very easily do that in C, right? And so this is a key difference between a memory safe language and a memory unsafe language. And C is memory unsafe. When you want to achieve memory safety in the managed languages that you've used before, such as Java, TypeScript, Python, there tends to be a trade-off of performance. When you're trying to access an index of an array in Java directly, it's going to have an extra check in that access to C if this is a valid memory address per the memory that was allocated for this particular array. And if not, it raises that exception, right? But there's that extra check that it's ensuring the safety by giving you an extra check at runtime. And there are other examples of this as well. And when it comes to, we'll look at dynamic memory and the lifetime of things that are objects and arrays that live on the heap dynamic memory space. There's garbage collection, which we'll talk about in more detail when we get to it. But there's a whole background process which is going on, which you generally have not had to have any concern about, that's sort of cleaning up after you. That takes some time and performance to have garbage collection in a language. There is a performance trade-off there. Whereas in C, it's going to be on you and us to clean up any memory that we allocate dynamically ourselves. And that comes at the cost of us needing to do some extra work. But we can almost always guarantee better performance if we could implement and had a high degree of confidence in the safety of what we were doing and the validity of our strategy for maintaining memory. For modern systems programming languages, and Rust is a leading contender here, the way that Rust achieves memory safety while also being a systems level language that gives you direct access to memory is it requires additional annotations and syntax in the programming language. And Rust actually has syntax for specifying the lifetimes of various values and pointers specifically in your programs. And so there's this new syntax that you have to learn for working and explicitly declaring the lifetimes of certain parameters, for example, or just references and pointers that we don't do in C. But C doesn't give us any extra guarantees. What Rust gives you, by virtue of having this extra syntax, we're talking about lifetimes, is the ability to prove and check how you're accessing things. And you can prove that you won't have any unsafe accesses to memory. This is the big learning curve that you have to get over when initially learning Rust, but it comes with some really fantastic trade-offs. You don't have, if your Rust program compiles, you can be much more confident in its validity and its correctness than you can in a standard C program, right? So with C, we're going to have to think very carefully about what it is we're doing and very intentionally about the lifetimes of our pointers to values in memory. So just to give a couple of quick examples of this in the context of C, and with automatic memory. So these are going to be local values that are in stack frames. Let's look at an example here. The first question is, does this code compile? And the second question is, does it run? And the third is, what is its output if it does run? I'm going to give you a moment here, and I would encourage you to try thinking through this, reading through this code, and just sort of desk checking what is it that you expect this particular program to do, and what would you expect its output to be. Pause the video here, think through that, and then we'll continue back in about 5 seconds. All right, hopefully you were able to identify something that was particularly concerning about this example. Notice when we call the function foo in main, we reach this variable declaration for a local automatic variable named a, and when we go and access it, it hasn't yet been initialized. So this is hopefully something that you can recognize as a potentially scary and concerning thing. So the first question is, does it compile? And it turns out yes, this will compile. So what actually is the output when this program runs? Well, if we wanted to just conjecture about this a little bit, we could assume that this is garbage the first time. We don't know what values were previously in memory at this frame when this function call occurs. And then when we see that we call bar with 211, we would pass 211 to the local parameter x of bar, and this would get printed out. And then we call foo again. And so the interesting thing that happens here, which is a happy accident. You shouldn't depend on any behavior like this because a is undefined, and when you try and access a variable or an area of memory outside of its lifetime, you can't assume anything about the validity of what it contains. Its value should be considered garbage for all intents and purposes. It may just so happen that there's a happy coincidence or accident based on the subsequent usage. Right? And that's what's happening here. So notice we could compile this, and if we didn't have any specific error checking or warnings enabled, we wouldn't get any warnings at all. It says, okay, we're going to trust you, C developer. And so you run this, and then this is your first garbage value, right? This is a completely meaningless value, and it's just whatever was in the contents of the bytes of memory that A was assigned in this function call. So this is just whatever was left around in that memory before. But notice when we called bar and said, okay, well, we're going to use a certain space in this frame for X and give it the value of 211. The next time around when we accessed A, there is this happy coincidence that the same memory space and addresses that were allocated for X as the parameter of the function called a bar are the same ones C is trying to allocate on the stack for and assign the variable A to. And so by virtue of this, this strange occurrence, it looks like A now has a value of 211. The reality is it's just that was the last bit of, or those were the last bytes of data left in that position on the stack when this function call occurred, and it was a weird happy accident. But you should be very afraid to see that this is, you know, a program that compiled and actually had some output that really shouldn't, you should never assign any intelligible meaning to a garbage value. Or said more specifically, if you access a variable or a location in memory outside of its lifetime, its value you must consider undefined. And if there's anything particularly interesting there, it's a coincidence that you shouldn't trust is intentional, or could always be the case that that's what it's going to be, right? If you actually did compile this with warnings enabled, you would see that with the -w all, so all warnings, this particular warnings flag will tell you A is uninitialized when it gets used. And so it's trying to be helpful here. So one of the things that I want to impress upon you with GCC is that if you see a warning, you should treat it like an error. I don't know why they don't just call this an error. I think because they consider errors things that cause your program to not be able to compile at all. But for your purposes, if you see warnings, especially those about initialization and here uninitialized values, you should treat that as pump the brakes. Don't even try and run this program yet. Go back and fix whatever problem existed in your code. So this is quite scary. The value is trash, even though this program runs. It doesn't crash or anything. Like this is a completely valid program. It just has garbage output. All right. Here's another example, and I want you to think through this one once again. Here we've got a main function. We've got a function foo and a function bar. And I'm once again going to give you 5 seconds to think through this particular code listing and try asking yourself if you think it compiles, does it run, and what is the output. All right, so hopefully you realize that there's something kind of scary happening here, right? Where when we call, we set up a pointer a to point to an integer, and we're going to assign or initialize a to be whatever the result of foo is. And foo returns a pointer to an integer value. So that seems fine. So we jump into foo and we think about, well, what's going on here? Well, if we think about the frames just very briefly, so we've got our main frame, and it's going to have some space allocated for this variable or this pointer variable named a. We don't yet know what it is. And then we have this call to foo happening. And foo has this variable x, whose value is 211, and has this pointer y, which I'm just going to write has address of x written in it, right? So this is a pointer to, or y is going to point to x. It's going to have the memory address of x stored in it, right? And we see that we're returning y, right? So I'm going to go ahead and let's just hypothesize that x's address is like ox ab, right? I'm making this up, right? But we're going to say that x's address is oxab, and so y would have also had that value, oxab. And then when we return y, we're saying, okay, we're going to return oxab back to this point where a is initialized, right? So a is also going to have oxab as the address that it's holding. Well, when a function returns, the expectation is whatever was in the stack frame that you're returning from, that just gets cleared out, right? So the computer is free to reuse that particular space for the next function call frame or whatever comes after it, right? So now we should be a little bit concerned. It seems like oxab refers to an address whose lifetime has expired, right? So with the rules of an automatic variable, x was a valid variable when it was initialized, but it expired when it fell out of scope, when this function returned. And so, wow, this seems like this is pretty concerning. What happens when we try and print the contents of A? Well, we can jump ahead and see that 211 gets printed out as the very first line, because even though the computer is free to delete the contents of a stack frame, it actually isn't, that would take an extra operation. It would take extra effort. There would be wasted instructions in your CPU if it needed to go back and clean up every stack frame after it was done. So it actually doesn't, it leaves whatever was there. And when it returns, it says, okay, whereas the top of the call stack was here before, it's now going to be, moved back to the bottom of main, all right? And so all that data is still there. You can still read that value. And wow, it seems like if this is all you were printing out and you just tried this, it would seem like this worked. But you have to realize that this is crazy, right? Like this value belonged to a frame that is no longer supposed to be a valid frame, right? And we can kind of prove that this is a scary thing and it's not doing exactly what we think it should be doing in the next section. So we call bar, right? And so what does bar do? Well, bar sets up 4 integers, an array of 4 integers, right? And it doesn't do anything else. It initializes those 4 integers and it immediately returns. It's a void function. All it did was allocate this array on the stack and return. Well, when we go to print, well, what is stored in this particular memory address? It turns out, and if we wanted to think about why, just very briefly, remember if Z's lowest address is for index 0 at the bottom, then its last address is going to be the one closest to the top of the frame, which would have been also where, just by coincidence, X was allocated in the foo frame. Right? So these details are things that are a little bit beyond our concern, but the reason why 94 gets printed out is because it was the highest order, the last element of this array, and because arrays have their 0th index allocated at the lowest position of, or the lowest address of the sequence of addresses that belong to that array. The very last address is the one that was taking the same place as X in the previous function call for foo. Again, though, this is a happy coincidence, or I should say a frightening, horrifying coincidence, and you should never trust that reading a value or a memory address outside of its lifetime gives you anything meaningful back. This is a coincidence that starts to give us some, what's interesting about this coincidence is it starts to give you some, we're piercing through the abstraction of the call stack a little bit, and you're starting to see how we can see through to how the call stack is implemented in this way, but we really shouldn't be able to. This is pretty horrifying. If we compiled this with warnings, what we would see is that all it tells us is there's an unused variable z, right? It only complains about this bar function. It doesn't complain at all about returning a pointer that pointed to a local variable in a stack frame, which is something you should never do, right? And so, wow, that's pretty scary. This didn't even give us a warning about the thing that it should have, about the really dangerous thing going on in this program. Right? So this is a fully insane and pathological demo. The key takeaway here that you should remember about lifetimes in automatic variables is that you should never return a pointer to a local variable, right? You should never return an address of a variable that was allocated in a frame to some other frame, right? So this is something you should never do. All right. One more example, just as something to think through. And once again, the same three questions. Does it compile? Does it run? And what is the output? And in this case, we're thinking specifically about line 20. And you're not necessarily supposed to know this, but I'm curious if you can reason through, based on some of what we've talked about before, what might be the expected output there. All right. So we've got a pointer that's declared at the top level of the main function, and its name is p, right? And then notice we've got these blocks established. And remember, the important thing about these blocks is any variables declared inside of a block is scoped within that block explicitly, right? So the scope of this variable I and the memory that it's associated with begins on line 7 and ends on line 12, right? So what happens here? Well, we initialize I to be 0, and then we say, okay, p, the pointer p is going to be assigned the address of I. Now, this should already be setting off some warning flags. Notice that the scope of p, where we can access p, is greater than the scope of I, right? So p is local to main, so we can access p at any point in this segment of the program from its declaration on, and it's specifically valid after it's been initialized. But if we try and access p after the memory address that it references has expired, or after its lifetime has ended, then we're going to have some memory unsafety, and we should be concerned about that. So anyway, we print I and the address of I, and then we enter a new scope. And notice here, we're just setting up a scope who has a single variable declared and initialize it named j. We print j's value and print the address of j. Notice that we didn't change anything about p. We didn't reassign the pointer p in this scope at all. And then the last thing we did was we printed out p. So let's take a look at what happens here. And with respect to the first question, does it compile? Yes, it compiles. And even with warnings, there's no warnings that are going to be emitted to tell you there's something you should have been concerned about or careful with here. So this is an example of an invalid access related to lifetimes that the compiler doesn't catch and doesn't protect you from at all. So this is why we have to be very careful and intentional about this. So let's see what's going on here. Well, I is 0, we print the address of I, and it's this long hexadecimal memory address. That sounds fine. and we then initialize j to be 1. And notice when we print j's memory address, right, the address of j, what the compiler did was it said, okay, well, we set up the scope and I was valid in it. It was an integer. We finished that scope. So when we go into the scope where we have j, why don't we just reuse that same space that we were using, that same address that we had for I? That's a totally fine thing to do. In fact, it's a pretty efficient thing to do. We don't need to use more memory because the scope of I is completed. But we reassigned that memory address to be 1. And when we went and finally printed P, notice that it had the value that was last assigned to J in it, right? Because J was what assigned or bound to that same memory address in our frame. And again, that's a happy coincidence or a scary one, depending on how you look at it. The key thing to recognize here is that we should never, ever, ever, ever access a memory address outside of its lifetime. And here we're doing that. And notice the compiler was no help to us whatsoever. And the key thing that we're looking for with an automatically allocated variable, right? And so that these are automatic variables, and these are even more nuanced than variables that are just local variables to a function. These are local to a block within a function, right? And so remember the scope of I. So I is a variable whose the memory address associated with it is valid. The lifetime begins on line 8 when we initialize it to 0, and it expires on line 12. But we assigned its address to a pointer whose lifetime exceeded that duration. And that's where you've got to be careful. If you are setting up a pointer and giving it an address, and that pointer lives or has a lifetime that's longer than the address you're assigning to it, that's a smoking gun for you're probably going to have a memory error in your program, and you should be careful not to do that. All right. And so the notes in the slide kind of refer to this. So you've got to be very careful to be intentional when you're assigning the address of some variable or array or index within an array to some other pointer or returning a pointer. You need to have confidence that that memory is going to be valid for as long as the pointer is, and that those lifetimes are going to need to be tied to one another. All right. So we looked at these 3 examples, and for reference in the slide deck, I just want to point out that if we're thinking about what are the lifetimes of each of these variables, well, in this foo, the very first example we looked at, this foo function, A's lifetime is non-existent. It was never initialized, and so if you never initialize a variable, it's never valid to access it, and so it was a variable that never really had a lifetime, right? So it's never been valid. If we think about X in this example, where we're talking about what is the lifetime of this variable X, and this variable X was initialized to be 211 here, and then so X had a valid lifetime starting at line 20, and then it ends when it falls out of scope, right? And so the concern here was, well, we returned Y, which was an address of X that caused a leakage of that memory address outside of the scope of its validity, right, or outside of its lifetime, right? And lastly, what is the lifetime of I? So this is the example we just looked at, and just to remind ourselves real quick, its lifetime did not begin on line 8, right? So a lifetime begins when it's valid to access a particular memory address, and so I's memory became valid at line 9, and then it expired at line 13, right? So we wound up referring to the same memory address later on in a way that was invalid, right? So the key lesson here with lifetimes is you never want to access memory outside of its lifetime. If you do, the result that you get back is undefined. It has to be treated as undefined. You may coincidentally see something that looks right the first time or looks right by accident, but it's important to realize that you're getting back a garbage value, and this is a memory error. technically is how you should consider it. So when we looked at A here, when we printed A, this is undefined behavior because we're reading A outside of A's lifetime. A was never valid. It had no lifetime because it was never initialized. When we returned X, or the address of X in the second example, which was assigned to the pointer Y, right? So when we return that address from foo back up to the main function, right? So this is where that happened. And we later accessed A. Notice we accessed X, or the memory that was assigned to X, outside of its lifetime. And so that's a memory access error. And so you never want to dereference a pointer outside of the memory address that it was set up to refer to its lifetime. And then in the last example, which we looked at most recently, we have this pointer P, and it really was assigned an address that was only valid for where I's lifetime was valid, so lines 9 through 12, right? But we wound up reading it down here on line 21, so outside of the valid lifetime, and that's why this was not memory safe and had a memory error in it, right? So what we're seeing in this video is an introduction of the concept of lifetimes. And we looked specifically and exclusively at automatic variables, which are local stack variables. In the next video, we'll look at static variables in the lifetime of static values. And in the final video on this concept of lifetimes, we'll look at dynamic variables, or dynamically allocated memory, which is what we call heap memory. And we'll look at malloc, which is a memory allocation function that's standard in the C library for allocating some memory in a storage space that we're going to have full control over its lifetime. And so these are the three lifetimes that we need to be very considerate of when we're writing systems level programs in C. In automatic variables, the key things to recognize are a variable that's automatic becomes valid, or its lifetime begins once it's initialized, and once that memory that it's bound to has some contents in it that you intentionally put there. And a memory lifetime of an automatic variable expires when that variable falls out of scope, and any access to the address that was previously assigned to an automatic variable outside of its lifetime or after it has expired should be considered undefined behavior, and anything that you read out of it will be garbage values, right? So we'll look at those next, and for now, this is lifetimes of automatic variables.